All right, get excited. This is our last set of notes for our forces unit. Whoop, whoop. All right, so today we are not necessarily doing anything huge and new. All right, we're just diving deeper into the force of friction. We've been using friction this entire unit. All right, so a lot of this stuff you have already heard me say, we've already been working with. All right, but you do need your calculators for this. We do have some new equations. All right, so all today we're going to be talking about friction. We know that friction is an oppositional force. All right, so it's always going to oppose the motion. So friction will always be, friction will always go in the opposite direction of the net force, which is also where the motion will be. So if your object is moving to the right, friction's going to go to the left. If your object is moving up, friction is going down, so on and so forth. All right, so whenever we put numerical values with the force of friction, it is only decided by two different things. All right, so the first one, which is big, is the type of surfaces in contact. Obviously, rubber and cement is going to have a different amount of friction than, say, like ice skaters, ice skates, steel on ice. All right, so two very different substances, two very different situations. All right, so it's going to depend on the type of surfaces in contact with each other, but also the amount of force pressing the surfaces together. Think about what is causing those two objects to come together. All right, so again, whenever we are putting numerical values with friction, frictional forces can actually only be estimated or approximated because, to the naked eye, what we see is a flat surface on another flat surface. But if you get into like the microscopic levels, then you see that really the only parts of the surfaces that are touching are those two little parts right there. So it's those two little parts in this little part right here, this little section right here, that are actually causing that frictional force. All right, so on this one, all right, we have a box that is on a horizontal shelf, all right, a level shelf. Well, those two from the naked eye's perspective look like they are smooth surfaces. But again, if you get to that microscopic level, it's just going to be these few spots that are actually causing all of that friction. All right, and so those spots where they actually intersect, where they meet, are called micro welds, and those are the only spots that are causing the friction. All right, so once again, we can't see that whenever we are calculating the amount of friction. So the frictional forces that we calculate are just an approximation. All right, so again, coming back to this, we're going to come back to this a lot. The two things that determine the amount of friction that's happening between two surfaces is the type of surfaces and also the amount of force pressing the surfaces together. All right, so this tells us, oh no, it's not. Come on now. There it goes. All right, this tells us that friction is independent of the surface area. All right, so let's say that we had a bike tire and a car tire that were made up of the exact same material and they were on the exact same surface. Well, if they have the exact same amount of force pressing down on them, then they will have the exact amount of friction acting upon them. All right, so your surface area, how much of that substance you have, does not matter. The only two things that matter are the two surfaces, what they're actually made up of, and then the amount of force that is pushing those two surfaces together. All right, so everything that we have been doing, all of the frictional forces that we have been using have been between surfaces that were moving against one another. So an object was sliding on another surface. All right, and that is the first type or the first category of friction, and that's called kinetic friction. Kinetic friction happens between two surfaces that are in motion. All right, so there is sliding happening. All right, so that's a big one. But we have also seen an example. We've actually seen this several times where we have had an object that's been on an inclined plane that was not moving. All right, so whenever we draw the free body diagram, we know gravity goes straight down. Our normal force is always going to be perpendicular to our surface. All right, so our normal force is perpendicular to our surface. Well, it's gravity that's wanting to pull that crate down that inclined plane, but friction is stopping it. We've talked about how friction is keeping it from going. So we have drawn this as our frictional force that's going back up the ramp. But because this box is not moving, it can't be kinetic friction. All right, that type of friction is called static friction. All right, so static friction is the type of friction that is occurring between unmoving objects. So say you are trying to move a very large refrigerator. All right, so if we draw the free body diagram, all right, we know gravity is pulling down, normal is pushing up, they are equal to each other. Well, say you are applying a force of 40 newtons. Well, if the refrigerator is not moving, that means that it is at rest. And if something is at rest, we know that the forces are balanced. So that tells us that our static frictional force is going to be a negative 40 newtons. All right, so it's balancing it out because it's not moving. All right, well, what if I increase that applied force to 60 newtons, but it still doesn't move? All right, well, that means that my static frictional force has gone up to negative 60 newtons. All right, but what if I increase my friction or my applied force to 65 newtons, and that is the exact amount of force that causes that refrigerator to start moving? That means that my maximum static frictional force is going to be negative 65 newtons. So that would be my maximum static frictional force. Okay, so our frictional forces, I want to go right here first. We'll pop back over there. Our static frictional force is equal to the amount of force needed to set an object in motion. All right, so we just called that our maximum static frictional force. All right, so we saw 3 different static frictional forces right here. This one was whenever it was balancing out the applied force because it still wasn't moving. This one was the same thing. It had to balance out that applied force. It still wasn't moving. But this one, that negative 65 newtons, was that maximum static frictional force. That's the amount of force needed to overcome that static friction. All right, so once again, the only 2 things that determine the amount of friction between 2 surfaces are 1, the type of surfaces in contact with each other, and then the amount of force pressing the surfaces together. So let's look at just this part, the type of surfaces in contact. So like we said, rubber on cement is going to have a lot more friction than steel on ice. All right, well, how does that come into play whenever we're trying to calculate the amount of frictional force? I'm so glad that you asked. All right, so the reason or the way that helps, that is determined, bless it, is by using something called the coefficient of friction. All right, so our coefficient of friction, the symbol is a lowercase Greek letter mu. All right, so we have, it's a U with a hook on the front. We saw this last year in chemistry whenever we were doing dimensional analysis. This was the prefix symbol for micro. All right, so we saw this, but this is now our coefficient of friction. All right, this is our first non-unit scalar value. So that means that this has no unit and no direction. All right, no unit and no direction. All right, so this tells us how much friction is occurring between two surfaces. All right, so the higher your coefficient of friction, the more friction is going to be happening between the two surfaces, or between the two materials. All right, so think about our example that we've been saying. That rubber on pavement is going to have a much, much, much higher coefficient of friction than steel on ice. All right, it doesn't matter if the forces, like the gravitational force pulling it down, is the same. It's going to be two different surfaces in contact with each other. All right, so again, the higher the coefficient, the larger the friction. All right, so bringing us to our two new equations. All right, F of S is just our static frictional force. All right, it's our static frictional force. F sub K is our kinetic frictional force. All right, so that's what that F sub S and F sub K are. We can just generalize this as F sub F. Both of these are going to be types of frictional forces. So it's the same thing as just saying F sub F. All right, so then we have mu sub S and mu sub K. So that's going to be, the mu sub S is our coefficient of static friction. Mu sub K is our coefficient of kinetic friction. And then you'll notice that both of them have our normal force in it. So remember, what are the two things that determine the amount of friction between two surfaces? The type of the surfaces in contact, that's going to be determined by our coefficient of friction. And then we have the amount of force pressing those surfaces together. All right, so remember, the thing that's pressing those surfaces together is going to be that gravity and normal. All right, but what about here? All right, the surface is going to be perpendicular. So we're going to be looking at that normal force. All right, so our normal force is what we use to determine that. All right, so you see both of those in our equation. So like I said, this can be generalized by saying the frictional force is equal to the coefficient of friction times the normal force. All right, that's the generalized version of both of these. You will get all three of these equations on your quiz next Wednesday or next Tuesday, or no, just your next quiz and your test. All right, so again, you have to remember that our static frictional force is the amount of force needed to set an object in motion. And then say it's already in motion. All right, if we were to draw our free body diagram, we know that we have an applied force. Well, if an object is moving at a constant speed, we know that that frictional force and applied force would be equal to each other. All right, but one thing that we do need to know, I think I skipped over it, is that once we do overcome that static friction and it starts to move, it is no longer static friction happening. It's going to turn into kinetic friction. And generally speaking, our kinetic friction is less than our static frictional forces. All right, so if we were to look at this situation, all right, so we have a 7.3 kilogram box is at rest on a level table. It is at rest on a level table. All right, so we know that we have our gravitational force, we have our normal force, and they are balanced. But that's it. All right, we do not have anything pushing it. All right, so there's no applied force, there's no tension force pulling it. So because there is no force trying to push it this way, there is no frictional force having to work against it. All right, so the amount of static frictional force that is present here is 0. All right, there is no static frictional force because there is nothing pushing it, trying to move it, that friction has to work against. All right, now these next two problems, these next two slides, I want you to put stars by. These are super important. All right, so the first thing that we have a 24 kilogram crate is at rest on a flat floor. All right, so let's draw this free body diagram first. All right, so it's a 24 kilogram crate is at rest on a flat floor. All right, so let's go ahead and solve for the numerical values for this. All right, we know gravity and normal are equal. We have our mass. We know that Fg is equal to mg. So we're going to multiply 24 times negative 9.81. So 24 times negative 9.81 is going to give us a negative 235.44 Newton force. Well, if gravity is negative 235.44, that means that our normal force is a positive 235.44 Newton force. Okay? Now, we're still not done. It requires 74 newtons of force to set it in motion. All right, so we have an applied force of 74 newtons. All right, so we know that, remember we set up here, our static frictional force is the amount of force needed to set an object in motion. All right, so that 74 newtons is also our static frictional force, just a negative. Okay? So what I have asked you to find is the coefficient of static friction between the crate and the floor. All right, well, we know that we have our equation, that just one equation with mu sub s. So we know the static frictional force is equal to the coefficient of static friction times our normal force. All right, we have both our normal force and our static frictional force, so we can go ahead and solve this. To get our coefficient by itself, we divide both sides by our normal force. So our coefficient of static friction is equal to our static frictional force over our normal force. So that's going to be 74 newtons over 235.44 newtons. All right, so we have 74, divided by 235.44. Notice that we have newtons on top and newtons on bottom, so they cancel out. We are left with 0.31. So our coefficient of static friction is 0.31. Remember, this does not have a unit. We just saw that, why it doesn't have a unit. And then we know it's a scalar quantity. So no direction, no unit. It's just 0.31. Now for this, on that same crate, the same exact crate, it's now in motion. So we know that a force of 53 newtons keeps it moving at a constant speed. I want to know the coefficient of kinetic friction between the crate and the floor. All right, if we were to draw another free body diagram, all right, it is the same crate, so our gravity and normal are both going to be the same. We have our negative 235.44 newtons and then a positive 235.44 newtons. All right, and we know that we are applying a force of 53 newtons and it's going at a constant speed. So we know our kinetic frictional force has to be negative 53 newtons. All right, so if we're looking for mu sub k, we know that we only have one equation for that. So we know that our kinetic frictional force is equal to the coefficient of kinetic friction times our normal force. So we're solving for our coefficient of kinetic friction. Divide both sides by normal, and we get our kinetic frictional force divided by our normal force. All right, so that gives us, 53 newtons divided by 235.44 newtons. So we divide 53 divided by 235.44 newtons. That's going to give us a coefficient of 0.23. All right, so we know, so now we have our two coefficients. So if you look, our 0.31 is our coefficient of static friction. Our 0.23 is our coefficient of kinetic friction. If you look, you see that the coefficient of static friction is higher than the coefficient of kinetic friction, which tells us that it takes a lot more force to set something in motion than it does to keep something in motion. And then last but not least, we have our free body diagram. All right, so in this free body diagram, we have not been given any of our forces. We have only been given our mass and acceleration. All right, so, and our coefficient of friction. So we have to fill in all of the rest of our forces. So the first thing that we're going to find, if we are given mass and acceleration, is going to be our net force. So we have a mass of 5 and acceleration of 2. That's going to give us a net force of 10 newtons. We know that our acceleration and net force have the same direction, so it's going to be 10 newtons to the right. All right, so that helps us. So we know that our applied force is going to be 10 more newtons than our frictional force, but that doesn't really help us whenever we're trying to figure out the rest of them. All right, so the next thing that we're going to solve for is going to have to be force of gravity. So we know that our force of gravity is equal to mass times acceleration due to gravity. So that's going to be 5 times negative 9.81. We multiply 5 times negative 9.81. We get a negative 49.05 newtons. Well, this object is on a surface, so we know that normal and gravity are equal and opposite. So if gravity is a negative 49.05 newtons, our normal force is a positive 49.05 newtons. Okay, so we have gravity and normal, but we still don't know friction and applied. Well, luckily, we just got a new equation. So we know that our frictional force can be found by multiplying our coefficient of friction times our normal force. So that's going to be 0.1 times 49.05. That's going to give us a frictional force of 4.905 newtons to the left. And we know, thanks to our net force, that our applied force is 10 more newtons than that. All right, so that's going to make our applied force a positive 14.905 newtons. All right, so we're going to do some practice with this, but as always, if you have any questions, let me know.